The U-6 Beaver is a rugged aircraft with plenty of power for short-field barrier takeoffs. To make the best use of its power, the Beaver is equipped with a Hamilton Standard variable pitch, constant speed, counterweight propeller. First, let's learn why variable pitch is an advantage and how it works. Variable pitch means that the aviator can adjust the pitch of the propeller blades and thus control the amount of work it does. With a variable pitch propeller, the Beaver can climb in low pitch or cruise in high pitch. Let's see how variable pitch makes possible efficient use of engine power. When the engine is operating, the blades can be adjusted from low to high pitch, or they can be set at any point between low and high pitch. When the propeller turns at medium pitch, the air offers a moderate amount of resistance to its movement. If the pitch is low, much less air resistance is offered. And with the blades at high pitch, much more air resistance must be overcome by the blades. Pitch and the resulting resistance of the air to the turning of the blades affects the horsepower output of the engine. With pitch at medium, our engine speed is 1800 RPM. Now, if the pitch is increased to high so that more air resistance must be overcome, the engine speed decreases since the engine must do more work at the same throttle setting. With the blades at low pitch, engine RPM increases since the power plant has less work to do at the same throttle setting. The best way to remember how variable pitch is used is to compare it with a vehicle transmission. When climbing a hill, low gear is used to keep engine RPM at a high level, which permits the engine to develop its full power. When driving on level ground, high gear is used because there is less work to do, and RPM must be kept from going too high. When a Beaver is climbing, low pitch is used so that engine RPM is high and power output is at its maximum. With a Beaver flying in a level attitude, high pitch is used since there is less work for the prop and the engine would over-rev in low pitch. Remember this: at the same throttle setting, low pitch produces high RPM and high pitch produces low RPM. This is the key to how variable pitch is used. Now let's find out how it works. On this engine mock-up, the propeller mechanism can be readily seen. There are only two parts: the propeller itself and on the rear accessory case, the constant speed control, which is commonly called the governor. This governor is geared to the engine. Using a blade turning device, we can see what happens when blade pitch is changed. As the blades move to low pitch, this cylinder moves outward, and these counterweights are drawn closer to the cylinder. When the blades move to high pitch, the counterweights move away from the cylinder, pulling the cylinder in. Two types of forces operate the propeller. Hydraulic force moves the cylinder out, pulling the counterweights in and turning the blades to low pitch. As the hydraulic force is released, centrifugal force of the whirling counterweights pulls the cylinder in and turns the blades to high pitch. Here is how the combination of hydraulic and centrifugal force operates. The cylinder moves the counterweights by means of short shafts and bearings, which ride in slots in the counterweight brackets. The counterweight brackets are in turn linked to the blades so that as the counterweights move, the blade pitch is changed. Oil is forced into the cylinder, moving it outward. As it moves, the shafts and bearings ride in the slots in the counterweights, pulling the counterweights in and overcoming the centrifugal force which tends to pull them out. As the weights move in, the blades are turned from high pitch to low pitch. Hydraulic force has overcome centrifugal force. Now, let's release oil from the cylinder and see how centrifugal force takes over. Centrifugal force pulls the counterweights out. The shafts and bearings ride along the slots in the counterweight brackets and pull the cylinder in, forcing its oil back into the engine. The blades are turned to high pitch. Now let's examine the pump and valve mechanism of the governor, which controls the flow of oil to the cylinder. Oil is delivered to the governor at engine oil pressure. In the governor, a gear pump raises the oil's pressure to approximately 180 pounds. The high-pressure oil moves on to a pilot valve, which controls its flow to the propeller cylinder. When the pilot valve is closed, a relief valve prevents overpressure by allowing oil to escape back to the governor pump inlet. Here is how the pump and valves operate. With the pilot valve closed, oil does not flow into or out of the cylinder, and blade pitch remains unchanged. When the pilot valve moves down, oil flows to the propeller cylinder. The relief valve closes. As we have seen, when oil flows into the propeller cylinder, the cylinder moves out. The counterweights are pulled in and the blades move toward low pitch. When the pilot valve moves up, past the closed position, oil flows out of the propeller cylinder and back through the governor to the engine. This is caused by centrifugal force on the counterweights, which move out and pull the cylinder in, forcing oil out of it. Since the pilot valve, which in turn varies propeller pitch, can be controlled from the cockpit, we call the Hamilton standard a variable pitch propeller. Next, we will examine its second virtue, constant speed. What does constant speed mean? It means that once the propeller control is set for a specific engine speed, the speed will vary only slightly and momentarily, even though the plane makes a minor climb, or flies through turbulent air, or makes a shallow dive. Any flight condition which would normally call for a slight throttle adjustment is automatically compensated for. This constant engine speed is a great advantage to the aviator. In low-level flying, it is necessary to make many adjustments of attitude. However, with a constant speed propeller, the aviator does not have to worry about minor throttle adjustments. His mind is free to concentrate on his other flight controls. We have seen how the pump and valve in the governor changes the propeller's pitch. Now let's add the parts which automatically make these changes. First, there is a speeder spring assembly, which consists of a spring collar and is attached to the pilot valve shaft, and a spring above it, which puts tension on the pilot valve shaft. Then there are the flyweights mounted outside the speeder spring assembly. Their inner arms rest against the underside of the outer race of the pilot valve bearings. In operation, the gear pump, outer race of bearings, and flyweights all revolve at the same speed. The centrifugal force of the whirling flyweights is pushing up against the speeder spring just enough to hold the pilot valve closed. The condition we see here is called an on-speed condition. The propeller is holding pitch without variation. This means the beaver is flying straight and level. Now it starts to climb slightly. Engine RPM starts to drop as the plane climbs. At the same time, the flyweights slow down and lose centrifugal force. Since they do not push so hard against the speeder spring, the spring expands. The pilot valve moves down and oil is pumped to the propeller cylinder. The blades move to a slightly lower pitch. Since at low pitch the propeller has less air resistance to overcome, the engine turns more easily and regains its original RPM. The flyweights also speed up, developing more centrifugal force. Once again, they compress the speeder spring and close the pilot valve. The cycle we have just seen with engine RPM dropping, pilot valve open, and oil flowing to the propeller is called an underspeed condition, since the engine RPM falls below its original setting. Now let's watch the action as the Beaver goes into a shallow dive. With the plane descending, there is less work for the engine to do, so it tends to gain RPM. Here is how the governor automatically returns the engine to its set speed. As engine RPM increases, governor speed also increases. Increased centrifugal force causes the flyweights to tip outward. Their inner legs push the speeder spring up and raise the pilot valve. Oil flows out of the propeller as the counterweights pull the cylinder in and turn the blades toward high pitch. At high pitch, the blades are harder to turn, so the engine slows down. As RPM decreases, the flyweights move in and the speeder spring closes the pilot valve. The condition we've just seen, with engine speed rising above the original setting and the governor draining oil from the propeller, is called an overspeed condition. In actual flight, the governor is constantly and very rapidly shifting from one condition to another, something like this. The propeller is continuously making minor changes of pitch so that engine speed is held constant within a very few RPM of its setting. This is the meaning of constant speed. Once set, the engine speed does not vary. To change engine speed, the aviator simply adjusts the propeller lever to a new setting, and the governor automatically and constantly corrects to maintain the new RPM. The lever in the cockpit is linked to an adjusting device at the top of the speeder spring. This is called the speeder rack assembly. When the cockpit lever is moved, the speeder rack assembly changes the tension of the speeder spring. The governor adjusts the propeller's pitch until it finds the new RPM, then holds it constant despite minor changes in flight conditions. This propeller requires very little maintenance. Here are the important points. During daily inspections, a check should be made for leaking oil seals. With the cylinder extended, look for rough spots and excess oil on the piston. A severe oil leak is easily detected since considerable oil will be thrown onto the windshield. When an oil seal or gasket leaks, they must be replaced. Counterweights require frequent repacking with grease. Some counterweights have grease fittings, and a grease gun is used for repacking. If there are no grease fittings, repacking can be done by hand through the bearing shaft slots. During periodic inspections, the counterweights must be disassembled and cleaned in solvent. Inspect the shafts for wear and straightness. The bearings and bearing races must be closely examined for scoring or pitting, especially if you are operating in a dusty area. When reassembling the counterweights, double-check the positioning of the counterweight stops. They must be positioned exactly as specified, or the propeller will be out of balance. Here is a caution on the operation of the propeller. Whenever the engine is stopped, the propeller must be at high pitch. There are 3 reasons for this. If the propeller is left at low pitch, the piston surface on which the cylinder rides is left uncovered and exposed to dust, grit, and corrosion. Also, the cylinder is filled with oil, which will slowly seep back into the engine as the plane stands on the ramp. When the engine is restarted, the first oil pumped by the engine goes to the cylinder. The engine's connecting rods and bearings remain dry until the cylinder is filled. Finally, in cold weather, the oil in the cylinder will congeal to a very heavy consistency, and the propeller's pitch change mechanism will not operate until it is thinned out. Since the Beaver is always parked with the propeller at high pitch, it must be started in high. As the engine starts, watch the oil pressure and temperature. As soon as the oil pressure reaches 50 psi, the propeller setting may be moved to the low pitch position. However, the RPM should not be allowed to exceed 1,000 RPM until the oil temperature reaches 40 degrees centigrade. The Hamilton Standard Variable Pitch Constant Speed Counterweight Propeller is simple mechanically and easy to maintain. It provides increased blade efficiency, reduced engine wear, savings in fuel consumption, and improved flight characteristics. But these virtues are only possible if you fully understand how it works, so that you can maintain it in top operating conditions.